Hello everyone. I appreciate Lennard-Jones Group for the kindness invitation, and I'm happy to give a talk to share my research. This talk contains three aspects: the background of my research, theory of ion migrations in Halide perovskites, and several examples. It seems that solar cells are very popular in UK. I can see them everywhere. The front of cover is the photo I took on the train to Ely, and the left side and the right side are photos of the rivers of Great Ouse and Cambridge, respectively. Okay, there is a question: what will be the next generation solar cells? There are so many candidates, such as highlight perovskites, organic materials. This is the best efficiency of solar cells plotted by National Renewable Energy Laboratory. We can see that the best PCE of highlight perovskite solar cells rapidly reaches 26.1% since from 2001, from 2009. Besides, highlight perovskite have another advantages of low cost, which is important for its commercial load. So I think it might be the most potential candidates for next generation solar cells. What disadvantage limits the commercial load of highlight perovskites? That is instability. One of the most important instability is caused by ion migration under illumination and the electronic field. As as an optoelectronic device, it is impossible to cut off the connection to light and electricity. Professor Sam, Professor Saiful Islam confirmed the most easily diffusion ion species and the corresponding pathway. Their group verified that halide ions are the most easily diffusion one, with the assistance of corresponding volcanic defects. As mentioned before, ion migration would bring negative effects on stabilities. First, experimental experts usually use mixed halide perovskites to satisfy the requirements of bandgap for high efficiency. Under illuminations or electrical field, ion migration would induce phase separation, thereby leading to bandgap splitting and efficiency decay. Second, the ion migration process would give rise to the transformation of defect levels from shallow to deep. As we know, deep defect levels is boring in optoelectronic device because it converts energies from light or electricity to heat. Therefore, therefore decreasing the conversion efficiency. Last, long-term migration would induce accumulation of halide atoms near the electrodes and promotes the reaction between halide atoms and metal electrodes in inducing the corrosion of electrodes. So we should and we must solve the problem. A better understanding of this phenomenon would help us to solve the problem through a more reasonable method. First of all, the diffusion follows the Fick's law. The left side of this equation is proportional to d0 and this time, where the activation energy EA can affect the left term by the by exponential relationship. So I think EA is the most important in this equation. EA is equal to defect formation energy plus the energy barriers EB. Defects are unavoidable for all semiconductors. Why did we only observe the ion migrations in highlight perovskites? So I think EB might be more important than DFE in this phenomena. Okay, how to describe EB or highlight perovskites? Here, the total energy of system is equal to the energy of perovskites, the energy of migration ion, and the interaction between them. uh, the EB is equal to the energy difference between the saddle point and the value point of surface energy surface. So to simplify this equation, we write the EB equals to the difference between the interaction terms. Then we use the Lennard-Jones potential theory to describe the interaction terms. Then the energy barriers is related to the energy depth ED and the distance factors. The energy depth indicates that the energy released when two atoms form a chemical bond, and we adopt linear combinations, linear combination of atomic orbital cells to estimate them. It is similar to the band center cells in catalysis field. Next, distant factors is described by a simple mathematical relationship like this. Then combining two aspects, we extracted descriptors. This section is related to the electronic density of states. That means decreasing of mismatch of band centers would increase migration barriers EB. Does this series work well for highlight perovskites? This equation is similar to the D-band central series in catalysis field. The prerequisite of D-band central series is a highly localization of D-band. Then we check the bandwidth of electronic dots of highlight perovskites. Luckily, the bandwidths are narrower than those of D-band of transition metals in catalysis systems. Then we think that the theory might be suitable for highlight perovskites. Then we give four examples to show. We give four detailed examples. The first example, we check the band centers of CSPB3. We found that there is a big mismatch between s orbitals of lead and p orbitals of chlorine by using DFT simulations. Then we check the barriers. The barriers is extracted by CRNEB method. It is about 0.35 eV. This result is consistent with those results, and it also explains why we always observe ion migrations in highlight perovskites in experiments. Next, we check the band center of these three lead-based highlight perovskites and the corresponding migration barriers. The energy barriers EBs are rarely decreased with the increase of mismatch of band center levels. Then we apply the tensor and the compressive strain on the lattice. We also observe the same physical law. The second example, we calculate dose and and energy barriers of lead-free halide perovskites. This is the structure of double perovskites. Here we designed two paths. The path one, the pathway one is that the atoms migrate from here to here and finally to here. The pathway two is the atoms directly from here to here. That's the former part of the pathway one corresponds to the broken of FeCl bonds. So we should check the dose of iron and chlorine, although the center of this path is potassium. Similarity, we should check the dose of potassium and chlorine for the latter part of pathway 1. We found there is a good match. There is a good match between iron and chlorine. So the diffusion barriers of former part of pathway 1 should be much higher than the latter part. Also, our CNEB calculations verified this result. We also found that the EB of pathway 2 is 2.04 EV, which is almost equals to 1.61 EV plus 0.28 EV. This is because the former part and the latter part of pathway 1 corresponds to the broken of FeCl bonds and KCl bonds, where the pathway 2 indicates that both two bonds were broken. We also calculate a family of double perovskites with different B sites. There is a linear scaling between our described and migration barriers, similar to deep and central series, indicating that the series is suitable for halide perovskite systems. This is the third example. We try to suppress the ion migrations in lead-based halide perovskites. We introduce B-site doping strategies. The second example told us that transition metal might be work well for these systems. So we design a nickel doping systems and the migration pathway is like this. Similar results. There exists a good match between nickel and chlorine. So we think the barriers should be high and the CRNEB result agrees it very well. Furthermore, we found the energy of band center of chlorine is lower than the VBM of most halide perovskites. That means we can suppress the ion migrations by decreasing the mismatch of band centers without introducing deep defect levels. So it is theoretically feasible to enhance the stability without losing their efficiency. The last example, actually, it is the experimental version of the third example. My collaborator fabricated a series of B-site doping perovskites. The left figure is the ion migration barriers versus doping concentration X. The barriers increase rapidly with doping concentrations. Meanwhile, the efficiency PLQY is maintained at a relative high level. The example 4 is in good agreement with our example 3. To summarize, we explore the physical pictures of ion migrations in halide perovskites, and we propose a potential method to solve the stability problem. And last, I thank I appreciate my collaborators for their useful discussion and kindly help. I also appreciate Lennard-Jones Group again for their kindly invitation. That's all. Thank you. Thank you for listening.